Hello and welcome. This is going to be our lecture video for January 22nd. We'll start with a little bit of review. Here we have a function g of n. We want to find the inverse of this function. So one thing we're going to do is I'm going to replace the g of n part with a y. And just because I'm used to it, I always replace this n with an x. I just always want to do it with x and y. Next, I'm going to swap the x and the y and make this x equals 1 over y plus 1 minus 1. Technically, now we found the inverse, but we almost never do x equals equations, so we want to get this back to being a y equals equation. Also, if we want to put it back into function notation, then we have to get this y by itself. All right, let's try to isolate that y by adding 1 to both sides. And we get x plus 1 equals 1 over y plus 1. Now, to get that y out from underneath the denominator, a trick is to just multiply both sides by the entire denominator. Multiply both sides by a y plus 1 in parentheses. Because this would go to the top of this fraction and cancel out, and all I'd be left with on the right-hand side there is a 1. And then on this side, I've got a y plus 1 times x plus 1. All right, let's divide both sides by x plus 1. Now, write this up over here. We have y plus 1 equals 1 over x plus 1, and then subtract 1 from both sides, and I get y equals 1 over x plus 1 minus 1. Now we can put this back into function notation. The inverse of g of n, denoted by a negative 1 there, equals 1 over n plus 1 minus 1. You might notice something interesting here. The reason I picked this is that this is a very unique function in that it is the inverse of itself. And that's pretty rare. There's other functions that this will work with, but pretty rare that a function is the inverse of itself. So I thought I'd show you that one. All right, let's practice a linear combination. Let f of x equal 6x plus 5. Let g of x equal x squared plus 4. And I want to find an expression for 2f minus 3g of x. So first I'll rewrite this as 2 times f of x minus 3 times g of x. So it's sort of like we're distributing that g in, but that's not exactly what's happening. But we are allowed to rewrite it like this. Now I can replace f of x and g of x with their expressions. So 2 times 6x plus 5 minus 3 times x squared plus 4. And I can distribute in the 2. I could distribute in the negative 3. And I get 12x plus 10 minus 3x squared minus 12. And then combine like terms. And now, once I've done all this work, I like to rewrite the first line. So 2f minus 3g of x equals negative 3x squared plus 12x minus 2. And so here is an expression for this combination of the functions. Okay. Goal for today is to be able to graph radical equations. Why are we doing this? This will give us opportunities to practice our transformations and graphs and talk about domain / range restrictions. So sorry. All right. So let's revisit how we graph inverses. To graph an inverse, you take any point x comma y and you convert it to y comma x. So the inverse of the point 2 comma 3 would be the point 3 comma 2 would be right here. The inverse of the point 4 comma 0 would be 0 comma 4. 1, 2, 3, 4. Negative 2 comma 0 for that one. This would be at 1 comma negative 4. So that's the inverse of that point. And then this point, its inverse would be negative 4 comma negative 2. Now, one thing you'll notice is that when you do this, you make a graph that is symmetrical over the line y equals x. All right, so it can be helpful to maybe connect each point with its inverse, and you might see the symmetry is a little bit better. There we go. All right, so now let's graph y equals x squared and then graph its inverse. So hopefully we remember this graph, but if you don't, it starts at the origin. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And these graphs are symmetrical over the y-axis. All right, so I'll do my best to connect this up. This is the graph of y equals x squared. All right. So let's graph its inverse. So I'm going to invert every single one of these points. 0, 0 is a point that doesn't move when it's inverted. Neither does 1, 1. 2, 4 then becomes 4, 2. 3, 9 becomes 9, 3. And 4, 16 becomes 16, 4. Connect these up and we get that the inverse of this graph goes off this direction. Now these points, they invert down here. But what we might do is only keep the top part of this graph so that this stays a function. So let me put a dotted line down here. All right, now let's find the inverse algebraically. So I would swap x and y. This would become x equals y squared. Then I take the square root of both sides to get y by itself. And I'll get that in red, I just graphed y equals the square root of x. So y equals the square root of x is the inverse of y equals x squared. So this is one way to graph. If you started with a radical, you could find its inverse, use our rules for graphing quadratics to plot those points, and then invert all of those points over the line y equals x by just flopping their ordered pairs. Like, let's do one example. 3, 9 became 9, 3. But that would be a pretty slow way of graphing. Better is to think in terms of graphing by transformations. So here is our standard form of a radical graph. Let's copy it down. This is standard form of a radical. And a, h, and k are working the same in this function as they have worked on every function so far. A is vertical stretch / flip. H is moving us left / right. And k is moving us up / down. All right, so if I wanted to graph y equals the square root of x minus 3, I recognize that this minus 3 is going to move us right 3. The parent function y equals the square root of x, well, we just graphed it on that other page, but it starts at 0, 0, it hits 1, 1, and then 4, 2, and then 9, 3. So there's your parent function. I'm not going to connect those. I'm just going to move each of these points right 3. So now I'm right here, 1, 2, 3, right here. I can only fit those 3 points, but now I can connect them, and that is my graph. And then you don't have to do this, but you can do the dotted line, other half of the sideways parabola, which we don't include because then this graph would violate the vertical line test and no longer be a function. All right, we want every vertical line to only cross a maximum of 1 time. All right, let's try that again with y equals the square root of x plus 4. This plus 4 is going to move us up 4. Again, dot in our parent function. We can remember the pattern 1, 4, 9, just like we remembered when we were graphing quadratics. This time the 1, 4, 9 though goes to the side, not up. All right, so each of these points moves up 4. So 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and then connect this. And there's our graph. And again, you can do the dotted line. That goes off on this side, but not required. All right. Now, 3 times the square root of x. That's going to be a vertical stretch. I said that this number could also cause vertical flip. That would be if this was ever negative. So again, a 149 going to the side. Vertical stretch means every point gets 3 times taller off the y-axis. So 0 doesn't move, but this was 1 tall, now it's 3 tall. This was 2, goes up to 6. That was at 3, goes up to 9. So we get a curve that looks like this, much wider, but still flattening out. All right, I'll embed a few more questions here. Let me also say, this would be a good time to start on the review. Your test is next week. The review is located on the extra stuff calendar. All right, that's it for me. Have a great rest of your day.